The following lecture covers the determination of phase diagrams. The determination of phase diagrams can be covered in a whole course all by itself, so this can be regarded as a very brief introduction to the subject. There is a laboratory exercise done in the computer lab utilizing fact-safe thermochemical software that we'll work with after this lecture. Let's start by going through the learning outcomes of this part of the course. After going through the lecture and the laboratory exercise, you should be familiar with what kind of data you need to construct a phase diagram. You should also be familiar with some methods that can be used to attain said data. And you should be familiar with the principle of the assessment and optimization of a system. In order to understand what type of data we need to construct a phase diagram, we'll consider an introductory example. For this purpose, we'll consider the lead-tin binary system. The binary phase diagram depicted in the figure was drawn using FactSage. In the figure, you can see that three different phases are present at different conditions. These are the solid solution of tin in lead, which is this one, FCCA1, and then you have the solid solution of lead in tin, which is this one, BCTA5, and then you have the liquid phase. And of course, the two-phase region with the combination of these phases. So, what kind of thermodynamic data is required to draw this? If we consider the system of lead and tin, the thermodynamic composition of phases at a given temperature is governed by the minimum Gibbs free energy of the system. To illustrate this, we'll consider a fixed temperature of T equals 400 Kelvin, which is marked by this dashed red line in the figure. At this temperature, the function describing the FCC solid phase can be described as the figure illustrates. So you have the Gibbs free energy here in joules, and you have the alpha here, which represents the A up here. So if A is 1, that means that we have only tin. And if A is 0, that means that we have only lead. So this is essentially the mole fraction of tin. Keep in mind now that this is the Gibbs free energy function of the FCC phase. To this function, we can draw a tangent at any composition. For example, this tangent. What does the tangent represent? Consider if we look at the intersection with the y-axis at alpha equals 0 and at alpha equals 1. At alpha equals 0, the intersection with the y-axis represents the partial molar Gibbs free energy of lead. That is the chemical potential of lead in the FCC solid solution at the composition where the tangent was drawn. Similarly, at alpha equals 1, the intersection with the y-axis represents the chemical potential of tin in the FCC solid solution at the composition where the tangent was drawn, that is here. In order to get the molar free energy of the solid solution, we simply sum the chemical potentials multiplied with the respective mole fractions. And if we do this, where do we end up? Well, you take this value right here multiplied by the mole fraction of tin in the FCC plus the value of this one right here multiplied with the mole fraction of lead, and the sum of these will actually be the molar Gibbs free energy right here. The significance of this might be unclear as of right now. Therefore, we'll introduce the Gibbs free energy function for the two other phases at T equals 400 Kelvin. In this figure, we have added the BCT phase and the liquid phase. So you still have the Gibbs free energy function of the FCC phase right here, but we have added the liquid and the BCT phase as well, as a function of the composition, of course. Consider that the equilibrium composition at any given temperature is governed by the lowest overall Gibbs free energy of the system. Based on this, it's tempting to think that the composition of the system will be only FCC between alpha equals 0 and this composition, and then it will only be composed of the liquid, and then finally only of the BCT. But this is not correct. And why is this not correct? Consider if we draw this tangent that is valid for a composition of both the FCC and BCT. Then we ask ourselves again, what does this tangent represent? Now we have a tangent that is valid for two phases where the chemical potential of lead is the same in both phases. So the chemical potential of lead in the FCC phase is the same as the chemical potential of lead in the BCT phase. Similarly, the chemical potential of tin is also the same. So the chemical potential of tin in the FCC phase of this composition is the same as the chemical potential of tin in the BCT phase of this composition. If you remember basic thermodynamics from previous courses, what we really described here is chemical equilibrium. One way of describing equilibrium is that the chemical potential for a component is the same in every phase at equilibrium. Consider now this tangent again, the red dashed line. At any composition between alpha equals 0.18 and alpha equals 0.98, we can achieve a lower overall Gibbs free energy than any single phase represented by these three different solid lines. How do we see this? Well, the straight dashed line can be expressed as the following equation. The chemical potential of lead multiplied by the mole fraction of lead plus the chemical potential of tin times the mole fraction of tin. Of course, this does not mean that we have pure lead and tin in equilibrium. We have a combination of FCC and BCT in equilibrium, and the chemical potential of lead is the same in both phases, and the chemical potential of tin is the same in both phases. Therefore, this can be considered as a condensed expression. What this means is that a combination of FCC at composition right here at alpha equals 0.18 and BCT of composition right here at alpha equals 0.98 is rendering the lowest overall Gibbs free energy of the system. If we now go back to the phase diagram, we can clearly see what we have discussed in this slide. This common tangent here spanning between alpha equals 0.18 and alpha equals 0.98 is actually these phase boundaries here that differentiate the single phase region and the two phase region of the FCC, the BCT, and this BCT plus FCC. And the composition of the system between these two phase boundaries is actually a combination of the FCC of composition alpha equals 0.18 and the BCT of composition alpha equals 0.98. Consider now if we do this for all temperatures between 350 up to 600. Then we would have enough information to draw these lines and therefore the whole phase diagram. In order to understand this concept fully, we'll briefly consider other places in the phase diagram as well. The upper figure, it illustrates the Gibbs free energy of some hypothetical phases at a fixed temperature of T1, and the corresponding phase diagram with the isotherm T1 is shown here in the lower figure. At the temperature of T1, the liquid phase has the lowest overall Gibbs free energy of the whole system except at composition A. So at composition A, you can see that the Gibbs free energy is the same for the alpha phase with composition 100% A and the liquid phase with composition 100% A. And in the phase diagram, we can see that this actually represents the melting point of pure A. The next figure has a new temperature, T2, and the isotherm is shown here in the phase diagram. So at this new temperature, the Gibbs free energy functions are quite different, and we can see that between a composition of 100% A and 3, we will have alpha as the lowest overall Gibbs free energy of the system. And we can see this because we don't have any shared tangent in this region between alpha and any other phase. However, if we go to composition 3 and to composition 4, we see that a tangent between the alpha phase and the liquid phase can be drawn, and therefore in this diagram we can see that between these compositions we have a combination of the alpha and the liquid phase. Moving forward between 4 and 100% B, you can see that the liquid phase has the lowest overall Gibbs free energy of the system. However, when you reach 100% B or composition 2, you will see that the beta phase of 100% B and the liquid phase of 100% B has the same Gibbs free energy, and therefore they are in equilibrium and we have the melting point of B. The final figure here represents the temperature T4. The isotherm is shown in the phase diagram, and it is actually the eutectic three-phase isothermal reaction. And you can see how this is represented in the Gibbs free energy functions. Between 9, 10, and 11, if we draw a tangent here, we see that the tangent is actually shared by all three phases. So beta is in equilibrium with liquid, which is in equilibrium with alpha. And the composition of the phases at equilibrium can be read as 9 and the 10 and the 11. And this is also illustrated in this phase diagram. Based on these three figures, as well as the previous example of the lead tin system, we can say that we need data describing the Gibbs free energy functions of the pure components, of the solution phases, and of the liquid phase at different compositions. If we have these functions, we should be able to draw the phase diagrams. If we are convinced that we need thermodynamic data describing the Gibbs free energy, then how do we know G? The description of pure components is familiar from previous courses, and the expression based on the enthalpy, entropy, and temperature, which is this expression, is something that we have used many times before. If we go one step deeper, we can describe the enthalpy and entropy based on the heat capacity at constant pressure. These expressions are also familiar from before. Considering the enthalpy, we can utilize the chosen standard state and then calculate the enthalpy at a given temperature by utilizing the heat capacity at constant pressure. And of course, if we have phase transitions, we have to include these as well in the function. In case of the entropy, we can calculate the exact value, as by definition, the entropy is 0 for a pure component at T equals 0 Kelvin. Considering that we can describe the heat capacity based on the temperature, as in this expression, utilizing constants and power functions of the temperature, we can develop an expression of G for a pure component as shown in this equation. As we have seen when familiarizing ourselves with the binary phase diagram, we often have solution phases in both the liquid and the solid phases. These phases cannot be described as pure components, and we have to introduce new terms to account for the Gibbs free energy. In solutions, the total Gibbs free energy of the solution phase can be described as the Gibbs free energy for the chosen reference state plus the Gibbs free energy of ideal mixing plus the Gibbs excess function, so as given in this equation. And this is also something that we have gone through in a previous course. In the course of high temperature processes, we saw that for a binary system, we can express the ideal Gibbs mixing quantity as this function with the gas constant, the temperature, and the mole fractions. In the same course, we also saw that the excess function was described based on the mole fraction and functions for the activity coefficients for the components in the system. The excess function, this one, it can be broken down and modeled according to 4 different categories. These are the random substitutional models, the sublattice models, the ionic liquid models, and the aqueous solutions. And in this course, we will briefly go through these 3 first ones. So here we have the 3 different models, the random substitutional model, the sublattice model, and the ionic liquid models. So let's go through these 3 models, and we start with the random substitutional model. These random substitutional models, they are used for simple metallic liquids and solid solutions where components can mix on any spatial position which is available to the phase. In, for example, a solid BCC structure, this means that any component can occupy any of the atomic sites that represents the BCC unit cell. In a liquid phase, we don't have any crystallographic structures. In this case, the components rely on random substitution without any preferential occupation sites. An ideal substitutional solution is characterized by the random distribution of components on a lattice with an interchange energy equal to 0. This means that atoms can be substituted without a change in the energy. Thus, the excess function is actually 0, and the Gibbs free energy of mixing is that of the ideal mixing quantity presented in the previous slide. The ideal mixing energy can be related to the configurational entropy, but for the sake of this introduction, we'll skip that part. The assumption of ideal mixing can be valid in gases, but in condensed phases, there is always some interaction between components. We'll start by looking into dilute solutions. The simplest form of expressing the activity and in the end the Gibbs free energy of a dilute solution is via Henry's law. The activity coefficient in this equation is constant, so this is gamma I 0, and it is valid when you approach the infinite dilution. Although this equation can be valid when considering one solute, the application when interactions between multiple solutes are present requires another expression. For this purpose, the Wagner-Lupis-Elliott formalism or the VLE formalism can be utilized. In copper or ferrous-based alloys, there are substantial experimental literature available that presents the interaction parameters, which are these epsilon, which accounts for how the activity of one solute is affected when introducing another solute. These models are suitable in dilute solution, but have fundamental limitation when handling concentrated solutions. The regular solution model considers that the magnitude and sign of interactions between the components in a phase are independent of composition. Furthermore, the total energy of the solution is assumed to only arise from nearest neighbor bond energies. If the reference state is chosen as the pure components, let's say component A and component B, we get the familiar function for the excess function as shown here with the mole fraction of A multiplied by the mole fraction of B multiplied by this parameter omega. And the omega, it represents the temperature-dependent interaction parameter. The excess function, in this case, it attains this typical form for regular solutions as shown here. The regular model is the simplest of the non-ideal solution models. Being simple limits the cases where the model can be applied. An extension of the model can be achieved by introducing the composition dependency of this omega parameter. And this type of model is called the subregular solution model. So we'll leave the random substitutional models and move on to the sublattice models. A sublattice phase can be visualized by interlocking sublattices on which the various components can mix. So in this case, we have a lattice right here and an interlocking lattice of another component right here. These lattices are crystalline in nature, but the sublattice model can be extended to ionic liquids where mixing on ionic sublattices are considered. Sublattice modeling is commonly used in describing solution and compound phases. It's very flexible and can be applied for a variety of different phases. Line compounds are a group of phases where sublattice models can be used. These phases are characterized as phases where sublattice occupation is restricted by particular combination of atomic size, electronegativity, etc. Many examples of such phases occur in transition metal borides and silicides, as well as a number of carbides. Another group of phases is the interstitial phases, which commonly can be used to describe ferrous-based alloys. In the interstitial phases, the solute elements occupy the interstitial sides of the crystal structure of the solvent. A third type of phases where sublattice modeling can be used is the complex intermetallic compounds. These complex intermetallic compounds, they can have significant variations in stoichiometry. Many binary intermetallic compounds can exhibit significant solubility, whereafter several crystallographic sublattices have to be considered. The last example is the order-disorder transformation, which accounts for phases that can be ordered under certain conditions and disordered under other conditions. For example, in room temperature, the solvent and solutes can have strict preferences for lattice sites, whereas at high temperatures, disorder and random mixing across sublattices can occur. In terms of the last type of models, the ionic liquid models, slags and molten salts are typical examples where these can be used. The phase diagram of such liquids can be complex and show apparently contradictory behavior. If we consider the CaO-SiO2 phase diagram, which is shown here in the figure, we can see that we have both liquid immiscibility right here, and we have the formation of intermediate compounds. For example, this one, and this one, and this one. Why is this contradictory? Well, if you see the liquid immiscibility right here, it is associated with a positive deviation from ideality, whereas the intermediate compounds right here are associated with quite a strong negative deviation from the ideality. In short, in liquid immiscibility, the components don't like each other, whereas in formation of intermediate compounds, they like each other very much. This means that these phases have complex changes in Gibbs free energy with composition, whereafter simple mixture models for ionic liquids has not been successful. Four commonly used models to account for the thermodynamic behavior of ionic liquid are the cellular models, the modified quasi-chemical models, the sublattice models, and the associated solution models. These four models will not be covered in this introductory lecture. If you're interested, you can find information in scientific journals or in CALPHAD literature. That is CALPHAD, CALPHAD literature. Considering the present slide with these different models, it's clear that we need some sort of database where we have the thermodynamic description of the systems, which can be used to finally construct our phase diagrams. The question now is, how do we go from the thermodynamic data to the models that describe the system and therefore the phase diagrams? The first step in constructing a description of a system is by gathering available experimental and theoretical data, that is, making a literature survey. It's useful to categorize the data according to different types of measured quantities. For example, experimental phase diagram data, experimental thermodynamic data such as enthalpies, activities, chemical potentials, etc., crystallographic data, including point defects, vacancies, ordering, and so on. There's also theoretical papers available that should be included in the literature survey. After gathering the data, the information should be assembled and analyzed. The analysis concerns, for example, the detection of contradicting measurements and checking for appropriateness of experimental methods and determining the possibility of systematic errors. The most apparent contradiction is if different values have been reported for the same quantity. In such cases, you have to critically analyze chosen experimental setups, so maybe these setups don't reach equilibrium, or they have used an inappropriate crucible, which means that, for example, impurities may be present. After the data is assessed, an appropriate model should be chosen. A well-chosen model is characterized as one that has a physical background, for example, a sublattice, ionic lattice, or associate model. Furthermore, the experimental values used should fit the corresponding calculated quantities well, using only a few model parameters. After choosing a model, the optimization procedure of the model starts in order to reach the optimized description of the system. The first step in the optimization is to attain a set of parameters that roughly describe the main features of the data. After this has been achieved, the parameters are fine-tuned by an iterative process in order to reach the optimized description of the dataset with the model. The description of the adjustable model parameters is calculated using a least square fit routine. This routine minimizes the offset between the modeled and the measured values. The measured values are then compared with the modeled ones, and if the correspondence is good, then we're satisfied, but if not, we have to find means to improve the model. One way of doing this is by weighting of data. This concerns giving more weight to model fitting of experiments with low experimental errors as compared to those with reported larger errors. The least square fit method is affected by weighting of the data, whereafter this can be revised to achieve a better fit of the model. Another way of improving the model is by introducing model parameter constraints. Sometimes there's not enough information to describe a phase, which means that assumptions can be made. And there are different strategies to this, and these can affect the results of the model. Sometimes there might be contradicting data describing the same quantity, or you might have experimental datasets that fail to describe the physical reality. In both cases, the original literature should be consulted in order to deselect the faulty data from the values to be modeled. In other cases, it might not be the dataset that doesn't describe the physical reality. Instead, it can be the selected model that is not appropriate to describe the physical reality. Therefore, you might have to re-evaluate the model selection. If new experimental data has been attained, the model can be optimized considering this new experimental data as well. After the model describes the set of data collected from the literature in a satisfactory manner, we can move from this iterative process to the extrapolation into higher order systems. For example, if you have done this in the binary system, you go to the ternary phase diagrams. Sometimes the extrapolation from the binary to the ternary system does not explain the ternary experimental information. In this case, the ternary experimental information is used to improve the binary description. This new information is used to re-evaluate the description of the lower order system. And as you can see, then we move back to this one and we have to optimize it again. And when this procedure is done, we have reached our optimized description of the system. Now we can take a step back and briefly summarize what we've gone through in this lecture. So We convinced ourselves that we need the description of Gibbs free energy at different compositions and temperatures. We also found that we can model Gibbs free energy using different approaches and that we optimize this model to correctly describe the observed reality. The final question is then, how do we get the data and what type of data do we need? The first set of data can be categorized as common thermodynamic quantities, and these might include heat capacities, enthalpies, entropies, Gibbs free energies of reactions, activities, and chemical potentials. The second set of data concerns experimental phase diagrams. This type of information is essential in the optimization process of calculated phase diagrams and therefore predictions in multi-component solution derived from binary and ternary systems. Typical examples of information derived from experimental data is determination of cooling curves, phase boundaries, and crystal structures. There are several experimental methods that can be used in order to determine these type of data. Some of these experimental methods are listed here and includes electrochemical methods, calorimetrical methods, methods that are based on vapor pressure, X-ray diffraction, hot stage microscopy, equilibrium quench techniques, and differential thermal analysis, or DTA. We will briefly go through the principle and which type of data that can be acquired from each of these methods. In electrochemical cells, such as the one depicted in the figure, an electromotive force, or EMF, is generated which can be used to measure partial molar Gibbs free energies, that is, the chemical potential and therefore also the activities. In one cell, a pure substance of, for example, silver is fused in a salt electrolyte. In the other cell, a solution containing this substance, in this case silver, is also in the liquid state. The electromotive force arises from the difference in chemical activity between silver in the pure substance and silver in the solution. The electromotive force can, after this, be related to the activity. Apart from the activity and partial molar Gibbs free energy, that is the chemical potential, the partial molar enthalpy and entropy can be calculated from the generated data in the experiment. Also, these type of experiments can be used to gather phase diagram data such as determination of phase boundaries. The second principle is calorimetry. Calorimeters measures the heat transfer from a sample to the surrounding and vice versa. The principle is based on that isobaric heat transfer is identical with the change of enthalpy if no other energy is simultaneously transferred. Calorimetry can be used to determine enthalpies of solution, transition, and phase transformations. The vapor pressure techniques utilizes gas phase equilibria in which we know that the activity of component I in a solution is related to the vapor pressure of I in the solution divided by the vapor pressure of pure I. That is this expression that we have come across in the core high temperature processes. There are different techniques used to measure the vapor pressure, and these are suitable for different applications. However, in all cases, the thermodynamic properties to be determined is the activity. The technique of XRD is familiar as this is something that we introduce in this course. The way it can be used in determination of phase diagrams is as a supporting tool to determine phase fields, phase boundaries, and crystal structures. The lattice parameter given here on the y-axis in angstrom has been measured for different compositions of atomic percent in carbon in this hafnium-carbon binary system. The atomic range here of carbon is across a boundary between a two-phase and a single-phase region. The lattice parameter, it varies in the single-phase region, but is constant in the two-phase region. So if we consider the measurements denoted by these squares, which represents the data at 1400 degrees Celsius, if you increase the atomic percent of carbon, you are first in a region where you have a constant lattice parameter, which is given by these black squares. and then you have a region here with changing lattice parameter with increasing carbon content, which is given by these white squares, and then you come to this region again where you have a constant lattice parameter, again the black ones. And as we said, the lattice parameter change in the single phase region, so you can identify the phase boundaries as here 39.5 atomic percent of carbon at 1400, and here 49.5 atomic percent of carbon. Consider if you repeat this for a different temperature. For example, here you have at 1600, you will have a different composition for the phase boundary. And you can imagine that if we do this for multiple temperatures, we can draw the boundary between the single phase and the two phase regions. The fifth principle is that of hot stage microscopy. Hot stage microscopy is the utilization of a microscope setup with a hot stage. This allows visual observation of the sample upon heating or when subjected to a certain temperature over time. In a way, it's a combination of microscopy and thermal analysis. The method is suitable for compounds with low vapor pressure, and the data that can be acquired are solid-solid transformation, determination of liquidus temperature, and studying of solidification. The next principle is the equilibrium quench technique, and is easily illustrated with the following figure. A composition of interest is allowed to reach equilibrium at a certain temperature, for example here at T1, and it is then quenched and studied by, for example, optical microscopy or scanning electron microscopy. The micrograph here shows that we have a glass phase that was formed upon quenching of the liquid phase. We also have this crystalline phase, which suggests that we were somewhere in this two-phase region here. If we conduct multiple samples at different isothermal sections, for example T1, T4, T3, and T2, then you can imagine that we can determine these boundaries between the single phase and the two-phase regions. This technique is suitable to study solid-state equilibria and to find the liquidus temperature of high viscosity liquids. The last principle or technique is the differential thermal analysis, or DTA. This is a technique that is used together with thermogravimetric analysis, or TGA. A simplified setup for DTA experiments is presented here in this figure. The furnace, which is labeled 3, holds two crucibles labeled 1 and 2. The crucible labeled 1 holds a sample, and this crucible is connected to a thermocouple and a balance. The second crucible holds an inert reference material, and this crucible is only connected to a thermocouple. When the furnace is heated, the mass of the sample is monitored, and the temperature of the sample and the temperature of the inert material are monitored as well. A difference in the temperature of the sample and reference material will occur due to the difference in Cp value, and you will also have heat absorbed or released from this sample during heating. The results obtained in this analysis is shown here. The upper curve here, labeled Tg, shows the mass loss of the sample with time or with temperature. The second curve here, dTg, is the first derivative of the mass loss. And the last curve here, labeled dTA, is the recorded difference in temperature between the reference and the sample. The most common application of the DTA method in terms of phase diagrams is the determination of temperatures for phase changes. For example, liquidus temperatures or melting points. The reason for this is that the method is excellent in determining the start of formation of a melt from solids or start or formation of solids from liquid. Now that we have covered these different methods, we'll take a quick look at an example from a previous lecture. In the example, we were supposed to construct a hypothetical phase diagram that complied with these 7 criterion. So we had some melting of pure components, we had some melting of intermediate components, and we had some eutectic temperatures. The resulting hypothetical phase diagram is shown here. Considering the present lecture, you may very well see that the data given for this hypothetical phase diagram is something that could have been determined for a real binary system according to the method that we just covered. Furthermore, you can see that the data could have been even more specific in terms of the liquidus curves and the eutectic compositions and so forth. So we are moving towards the end of this lecture, and we will briefly look at the summary of this lecture and then the continuation of what we will do afterwards. We will conduct this summary backwards, that is, we will start at the end. The final thing that we went through was this different thermodynamic data and experimental determination of phase diagrams and different principles or methods that could be used to determine this data and the phase diagrams. Furthermore, we consulted how to construct and optimize models that constitute databases describing the different systems. We found that this was an iterative process and that the models are suitable for different types of solutions. The first thing we considered was determining the different lines separating phase field of the phase diagrams based on Gibbs free energy functions, that is, calculating phase diagrams. In this part of the course, we have no exercises in the book. Instead, we'll conduct a laboratory exercise in the computer lab. In this lab, we'll calculate binary phase diagrams using the thermochemical software FactSage. We'll compare these calculated phase diagrams to phase diagrams from the literature, and we'll ask ourselves, is the calculations always correct? I encourage you to start with the computer lab using the available instructions prior to the scheduled time. Doing so, you may resolve problems arising when we meet in class. However, I don't suggest that you sit for hours and hours not moving forward with the lab. In that case, you might as well work with other material in the course and you'll get the help you need when we meet in class for the computer lab. Let's end this lecture now by reviewing the learning outcomes that we specified in the beginning. After the lecture and the laboratory exercise, you should be familiar with what kind of data you need to construct the phase diagram. You should also be familiar with some methods that can be used to attain said data, and you should be familiar with the principle of assessment and optimization of a system. Please note the taxonomy or classification of the learning outcome of this part. You should be familiar with these concepts. The main goal of this part of the course, that is the phase diagram part of the course, is that you should be able to use phase diagrams, not to determine them or calculate them. However, knowing the thermodynamic background as presented in this lecture can help you achieve this main aim of the course. With that being said, we conclude this lecture and I thank you for listening. Remember to be sure to come by my office if you have any questions.